Class is going to start, everybody. Guys. Okay, very well. After this little technical glitch, let's continue this morning. Now with Tomas Reis from Geneva, who's going to tell us about semi-classical decoding renormalons.
Okay, hello. First of all, thank you for the organizers for inviting me. So welcome to episode 2 of the renormalon cinematic universe. Though here, I'm not gonna really talk about renormalons per se. I'll be focusing more on the integrability and Bethe Ansatz aspect of the things, and then Ramon will discuss a little bit more what we learned about renormalons from it. And here, I'm using semi-classical in a very broad sense of just trans series in a quantum field theory. So just a bit the structure of my talk. I'll start with a very gentle introduction to mostly just to set up some quick notation about resurgence in quantum field theory. Then again, a very gentle introduction to interval models, just for those who might not be experts in the topic. Well, I'm also not an expert in the topic, but those who might be less familiar with the topic. Then a sketch of what is this method, how do we get trans series and interesting resurgence information from integrability on its own. So as Marco was pointing out, one can combine integrability with other things, but really I'm just talking about using the Bethe Ansatz. And then I'll discuss some results in field theory. And time permitting, I would also like to discuss some results in condensed matter, which if you were in my talk at this workshop last year, it's a bit of the conclusion of some of the questions I set up at the time. So, okay, as far as gentle introductions go, I think this one's a bit too gentle. So I think we're all familiar now with these ideas, just to set up some notation of the Borel sum. So, okay, so the problem is in general asymptotic series in a resurgence. And I would just like, motivationally, I would just like to hold a little bit in this sentence, because these 2 points I think will be interesting as we move towards these techniques. These are really techniques that highlight these 2 great features of resurgence. On one hand, they let us make sense of these objects that we get in quantum field theory. And on the other hand, they let us explore. We learn new things by using these mathematical tools. We learn new physical aspects about quantum field theories. And ultimately, what we're looking for here are, when I say semi-classical decoding, is to write observables in quantum field theory with objects such as this, which of course we're all familiar, where there's a perturbative theory, which in general it's easier, and then some trans series sectors, where here I'm just being very epistemologically humble about what this trans series might be. The Z will eventually be the coupling, but I'm not assuming a lot of, a priori, not a lot of structure about these trans series parameters. Okay, so, and I want to study integral models. Now, if you have never heard about integral models, the 5-minute introduction, the 5 seconds might be a bit too much. The 5-line introduction, I think, is more or less gets it right. Is that an integral model is a very special quantum field theory where any scattering process can be factorized into 2-to-2 scattering process. So you have 3 particles, they meet, they collide, and then they scatter off, and you can get the exact same scattering, scattering matrix by considering that these 2 scatter first, and then those 2, and then those 2. Of course, this factoring, you can factor this in several ways. So you can also factor this first, and then those, and those. And this equality is highly non-trivial. This equality is essentially the physicist's description of what is called the Yang-Baxter equation, which is perhaps the defining equation of interval models. From a physical point of view, one way, if you want to develop some intuition about what is going on in an interval theory, is that in a regular quantum field theory, when you have a scattering process, you conserve the total momentum. So this would be the sum of the pi of all the colliding particles and the center of mass energy. So this would be roughly the sum of the momentum squared. You can think of integral theories as theories where you also conserve the sum of p cubed and p to the 4 and p to the 5 and so forth. So you can also think of integral theories as theories that have an infinite tower of conserved charges, which are so powerful that they let you simplify things, and ultimately the tower of infinite charges can be related to the Yang-Baxter equation itself. And I'm always here thinking about quantum field theories in 1+1 dimensions, or 2+0 once we weak rotate. And an amazing thing about interval field theories is that despite being highly restricted, you can actually get integral field theories that have very interesting properties that they share with highly non-trivial theories. In particular, you can find asymptotically free integral field theories. Now, this is of course very interesting because asymptotically free integral field theories will share many properties with non-trivial four-dimensional theories like four-dimensional gauge theories and QCD, as Marco was pointing out. So this is why they're so interesting. On one hand, they're at the Goldilocks level of not being too complicated, so you can solve it, but they're not too trivial. They're interacting theories with interesting properties that share important features with realistic theories. And so they're great toy models. And with this, I will never get tired of putting this quote by Freeman Dyson in talks. I think it's also a good motivation for the study of interval models. Well, now that he has spoken through me, I can go. We can keep going. So these are the integral field theories in particular that we're interested in. So there's Marco thankfully has already introduced all of them. So we have the ON Gros-Neveu model. This is a model, vector model of fermions. The ON nonlinear sigma model is a vector model of bosons. One can do the supersymmetric ON nonlinear sigma model, which is more or less the combination of these two. And they're bound together by a constraint. So these two interact with each other. And then we also have the SUN principal chiral field. Now all these models are asymptotically free theories. They have there's a dimensional transmutation, so there's a dynamically generated scale. There's a mass gap in all of these theories. They're all gap theories. And these gaps can be computed exactly. These calculations were done in the 90s by all of these collaborations that Marco also mentioned. And another important thing why I'm mentioning this is that really these mass gap calculations were already laid out a lot of the tools that then we built our method. Okay, and so how do we approach these theories? So we have an integral theory. What are we going to do with them? Now, so the idea is that we take our Hamiltonian and we couple to this conserved charge Q, and only some particles are charged under Q. So what happens is that once you do this coupling, so you can think of this as a chemical potential. Some people like to think about it as a magnetic field, because if you're using these integral theories to model some condensed matter systems, this would be actually more or less what happens if you turn on a literal magnetic field on your system. Or you can just think about it as a deformed Hamiltonian. But the idea is that once you turn this on, particles charged under Q will have this important negative contribution to the energy. So the ground state will no longer be the vacuum state. The ground state of the modified Hamiltonian will be a populated state of the original Hamiltonian. So now your ground state is a state which is populated by some finite number of particles charged under Q. So by controlling Q, you can also control which particles pop up. And integrability, thanks to this beautiful scattering of the S matrix, lets us write an exact wave function for such a state of particles going around in this 1+1 system. So you can think of it as particles going around on a circle and scattering in these nice Young-Baxter collisions. And this is the essence of the Bethe Ansatz equation. And as Marco pointed out, one can eventually massage it into this integral equation. Now, most of the elements have already been introduced in the talk just before. So you can think, so there's this parameter B, which essentially is encoding the coupling, but you can think about it as Marco was pointing out, it's some sort of Fermi level. It's the point up, and it's an energy scale after which there are no longer particles. We no longer have particles with energies above B. The theta is a rapidity, so it essentially encodes the momentum or the energy, and we have to solve for this epsilon with these boundary conditions. And K here is fully determined by the S matrix. So if you know the S matrix of your integral model, you can just calculate K. In some models, it might take some work, but it's a well-known calculation. So these equations are, of course, so this equation, it is an exact description of the ground state. Now, this equation knows all the physics about the ground state. I don't. Just looking at it. It's a highly non-trivial equation. It's somewhat deceptive. One can write it in one line, but actually decoding these type of equations is quite hard. There's an example which I'll actually show later in condensed matter of an analog equation, which to solve it perturbatively, it was a problem that was started more or less in the late 60s. And by 2016, people had gotten to the third perturbative coefficient. So it is very hard actually to solve these things in a weak coupling limit. And so even just getting the solution is hard, but then, okay, we get this wave function, what can we measure with it? And so here we get to the question of the observable. So Marco already introduced this very interesting observable of F, this free energy, which we then can normalize as this relative free energy, where we subtract the uncoupled case with from the chemical potential case, and we're essentially calculating the energy of the ground state, or the lowest eigenstate of our modified Hamiltonian. And this is something that one can compute in principle with Feynman diagrams. So this would be just calculating bubble diagrams. So one can connect, this is one of the advantages of the observable, one can make a very explicit connection with perturbation theory. And on the other hand, also as Marco has already pointed out, we can just also obtain it from this Bethe Ansatz integral equation that knows everything. So can we get this information out of the Bethe Ansatz integral equation? Now, a huge monumental step in the direction of extracting information from the Bethe Ansatz integral equation was the development of what is now probably called the Volins method that Volin developed in 2009. So I will not get into the details of this method, but the key step is that it reorganizes in the equation in such a way that when you expand it perturbatively, this integral equation becomes a set of recursive algebraic equations. So now this is something that you can just code Mathematica to do it. You can just code Mathematica to do it, and it has to recursively solve it, so you have to solve it order by order. It is not easy to solve it analytically, though the Budapest collaboration has done some important analytic progress on the O4 model. But this Volins method, you can just keep it running. Now, if you try to solve it, for example, exactly, by the time you get to the 50th, so coefficient 50, it takes about, with my code, it takes about 1 week to calculate one more coefficient. So it's really the marginal payoffs quickly decay at that point. But you can get to 50 coefficients, which is already much better than what you could do with Feynman diagram, for example. Numerically, one can take it much further. So we can usually take it, we took it to around 100, 200 coefficients. The Budapest collaboration has taken it to 2,000 coefficients in this particular case of the O4 model. So one can use this method really to decode a lot of perturbative information from this integral equation. And that's great. But this is the solution. This integral equation knows everything. It's an exact description of the ground state. So it should also encode the non-perturbative information. And this is what I want to talk about, is how can we get this non-perturbative information out, and what do we learn from it, and how does it interplay with resurgence? So the long story short is that I'm going to Fourier transform things, and I'm going to mention some Wiener-Hopf techniques. I'm mostly just dropping these names in case you are already familiar with the formalism. Maybe it will ring a bell. And ultimately, we'll be able to get a trend series for this observable f of h. So a very quick sketch of how this calculation goes. So I really just want to sketch the main ideas. I don't expect you to fully understand how the technicalities go, but once you get the main ideas, maybe if you see a similar problem, or if you're interested, you can go see the fine details in the paper. So what we're going to do is essentially take a Fourier transform of this equation, and then our ingredients will change a little bit. The Fourier transform of this kernel K, one can decompose it in 1 over a function which is analytic in the upper half plane and a function which is analytic in the lower half plane. So these, which I'll then G plus of minus omega, then sorry, here I call it G minus, but this one is just this one. And I'll put them together in this ratio in this function sigma. This will be our dramatis persona. This will be our main villain or anti-hero in a way. But the important point here is just to track the idea that this function sigma is just encoding information that we can calculate easily from the S matrix. So from the S matrix to sigma, it's more or less just complex analysis. G, I will not write out G because it has an ugly integral expression, but it's something perfect. It's something calculable from this driving term. And then Q will essentially encode in an indirect way. Q encodes a Fourier transform of epsilon. So if we solve for Q, we can eventually solve for epsilon. So this is our new equation after Fourier transforming and massaging things with this Wiener-Hopf techniques, where I have an equation for Q. There's this driving term that is somewhat under control, and then there is this integral here. Now we have an integral over the reals with this exponential factor here. So what we really want to do is to really deform this contour, to make this thing a convergent exponential, and so we get something that we can more easily control. And remember that we want to expand for large B. This will be our weak coupling expansion. And here we have our sigma. Now, sigma is a very weird, it's not that weird as functions go, but it's a particular function because it's a bit unpleasant. On one hand, somewhere in sine sigma, there are some logs that make it discontinuous along the positive and imaginary axis. So you really have to think about it in some Riemann surface. But at the same time, naively, it has, if you want, there's a thing with a discontinuity times something which has poles on the positive imaginary axis. So we have at the same time these discontinuities and these poles. So one has to be careful when deforming this contour. One has to be really careful about the interplay between these two aspects of sigma. On one hand, the discontinuity; on the other hand, the poles. And the long story short of this calculation is that so think about this as a Riemann surface, where sigma for the is continuous, is analytic. So here is our original contour, and so it is this dashed line here is the positive imaginary axis, but now it is discontinuous. I'm putting it on a Riemann surface such that we have two copies. We have this copy in the upper sheet, and we have this copy in the lower one. And these are the poles. So we have poles both because the poles are multiplied by something discontinuous. We have poles in both the upper and the lower branches, and of course the residues are different. Now we want to deform this so that it's close to the positive imaginary axis, because we want this to be exponentially damped. So we want to keep omega here positive imaginary. So we want to keep it an epsilon angle away from the positive imaginary axis so that we can take this epsilon angle to 0 in the end. But the sign of this epsilon angle is absolutely critical, because if we put this discontinuity slightly to the left or slightly to the right, we'll either pick up the poles in the upper branch or in the lower branch. Now, of course, this might already be sounding a lot like the sort of manipulations that appear in resurgence and in Borel summation, and this is perhaps not a coincidence. So in the end, the point of that drawing is that we can turn this integral into an integral along the discontinuity, where here this plus minus encodes the sign of this angle from the positive imaginary axis, plus some contributions from the poles, where here the plus minus has to be coordinated with this plus minus, because here the plus minus is choosing whether the residues are from the lower branch or from the upper branch. Now, there are a lot of calculations in the middle, because one still has to then use this integral to solve for Q. But the long story short, and skipping some pages of calculations, is that this discontinuity integral essentially becomes perturbation theory. So this will give you the perturbative series. And once you start expanding at large B, this expansion will be completely ignorant about this angle, while these residue contributions will become transmonomials. They will be exponentially suppressed in large B, where this chi n comes just from the position of the poles of the function sigma. Then this parameter C plus minus, and of course the notation is already giving you a bit of a spoiler of what's going on here. The plus minus is inherited from this choice of the residues, whether you are in the upper or in the lower branch. And then they will also have perturbative corrections on their own, because one will have to solve for Q, and Q is corrected, has perturbative corrections from this integral. So then this also has non-trivial perturbative corrections. And so in the end, this type of contributions, once we calculate f of h from that integral with Koch, what we get in the end is a transseries. Now, these residue contributions will become this, part, we have the perturbation theory here. This comes from the discontinuity integral. This comes from the residue contributions. And then somewhere in the middle, in the calculation, there's an unfortunate residue, but actually fortunate in a way, a residue at omega equals I that gives this single transmonomial here, this term here, which also has some ambiguous transseries parameter. So this is what I'm going to call the IR renormalon. I'm not exactly explaining why I'm calling it the IR renormalon. It will become a bit more clear in Ramon's talk. And these are just genuine non-perturbative sectors. So we get the transseries. We start from this integral equation. We do this Wiener-Hoff formalism. We just follow what complex analysis is giving us, and in the end we get the transseries solution. Now this special term, it is related. It is a bit related to this F0 subtraction, but there is also some important resurgence properties about it because there is an ambiguity in this transseries parameter. And so, of course, now we got the transseries, and of course I have to go. Yes, yeah, sure.
Wouldn't I expect that there should be also a tower of renormalon?
Yes, that will be Ramon's talk. Yes, yeah. No, but this is, I mean, of course, this is a very natural question. And so far, I've also been extremely neutral about the model. I mean, all these calculations, I only have to know sigma from k, but this I know from any integral model where this Bethe Ansatz description equation can be written. So these epsilon k's here, I'm not assigning any physics to them yet because they're going to be contingent on the model. Also, another point here, I'm writing things in G just because I think it's a bit more clear for the people familiar with the physics literature. In our actual calculations, we write things in alpha that Marco already introduced. Okay, so of course, one important thing is, okay, perhaps, I mean, we are physicists, perhaps you're not completely confident on the rigor of our manipulations. So we get the transseries. Of course, we should test this. This is something one can test with numerics. Because again, this integral equation knows everything. It's an exact description. It's also just an integral equation. One can numerically solve it. One can solve it numerically, and in many cases it is not such a hard test. Eventually, it might have some subtleties, but it's something which is doable on your own laptop. You can solve this integral equation in your own laptop. And so one can test a lot of things. First, we have all this perturbative data from Volin's method. So we can just look at the large order behavior of Volin's method of this perturbative series that we get with Volin's method, and check that indeed, for example, the ambiguities from Borel summation do cancel with the ambiguities from C0 and C1. Now here, we are doing very much sort of baby level resurgence. With the data that we have, we can only test the leading, so we can test C0 and C1, and in some special models, we can test C2. The problem is that this method, computationally, it is more or less as hard to push perturbative orders as it is to push non-perturbative orders, which is somewhat hard. So from this method alone, without Volin's method, it is not so easy to push perturbative orders. So here, we can at most get 1-2 terms. We cannot get a lot of data about these non-perturbative sectors. This is something that perhaps Janu's talk will give some more insights of how to go beyond what we did just from this Wiener-Hoff manipulation. So because we don't have, sorry.
Psi k, which is sitting the.
Oh yeah, so sorry. So these are the positions of the poles of this function sigma, which is determined by the S matrix.
Can you relate them to instantons?
Yes, that will be the next part of that. I'll then specify in each model what these psi k's seem to be telling us about. And so because we cannot push these series very high, we cannot really test. I mean, we cannot do very complicated alien calculus. We mostly can check the leading exponential terms, but we can check both from the side of, well, checking that indeed the Borel summation of this transseries is a well-defined object, and that the large order behavior does match the discontinuities of the CNs. And on the other hand, there will be some parts, like for example, C1 and C0, they have a non-ambiguous real part. This is just a straight up non-perturbative contribution to the result that you cannot get, I mean, you cannot get naively from perturbation theory. Of course, once you know the structure of the trans series, you could fit it. And we can also compare that then to the numerical solution of the integral equation and check that indeed these two aspects of the trans series parameters match. On one hand, there were also the discontinuity of Borel summation, and on the other hand, the genuine exact solution that comes from the integral equation. So here, just a matter of doing some numerics, and all these tests that we did with these results in several models, they always match. So as far as we can test, this is indeed the trans series expansion of this observable. Okay, so now the question is, what are these psi k's? And to discuss these psi k's, we have to zoom in a little bit on specific models because they will depend on which model we're talking about. Now here, I'm going to do a very naive separation of renormalons and instantons. Marco already talked a little bit about this. Ramon will go a little bit in more detail. But for the purposes of our discussion, I'll call renormalons anything that survives at the large n limit, because this is not, of course, the rigorous definition. The rigorous definition of renormalons is that they're tied to a factorially divergent series of diagrams, as Marco was explaining. But a usual signature of this divergent family of diagrams is that they survive at the large n limit, also as Marco already explained. While instantons, I'll call instantons things which are essentially proportional to n, so that in the large n limit, they just do not contribute. These will be correspond to Borel singularities, which would disappear at infinity, which are traditionally associated with the factorial growth of diagrams. Okay, so let's start with the ON nonlinear sigma model. So this is the Lagrangian. So we have some. It is essentially a model that takes values in the sphere Sn. This is a vector model of bosons. And here, so we have this, I'll call zeta IR the singularity associated to this first term, the IR, I'll call this the zeta IR. And I'll associate these things with this chi k, I'll associate this with the zeta k. So this, here I'll write the results in terms of singularities in the Borel plane. So we have this first IR renormalon, and then we have these singularities. And then we have these singularities, which are proportional to n minus 2. So here we're assuming that n is larger than 4. So this thing survives at large n. And indeed, it featured in Marcos's calculation. These ones, we know that there can be unstable instantons in this model. And so we associate these singularities seem to be consistent with unstable instanton effects. So for example, there are leading contributors there. For example, the first instanton of this kind, the trans series parameter is pure well, here it actually depends on the end, but they seem to be as far as we can tell, they are consistent with unstable instantons. So
Sorry, Tomas, what
yeah.
do you mean by unstable instanton?
In the sense they have a negative mode. So they are not true minima of the action in the sense. They're just some saddle points that which has some tachyon mode.
So complex
systems. They are at real actions.
If you do the steepest descent correctly, you pick up always the stability region, but you have to move away.
Yes, I think so.
If you stick on the real, you will call it unstable.
Okay.
Okay.
But for the O3 nonlinear sigma model, the O3 nonlinear sigma model, which Janusz will discuss probably in a lot more detail, is a more particular case, because here this is a model where we know there are stable instantons. And how does this manifest at the level of the Bethe Ansatz? What happens here is that we have the calculations go slightly different, and the end result is a bit weird. So we get perturbation theory, this F0. Then we get a single constant, effectively m squared. But if you rewrite m squared in terms of the coupling, this would be just exponential minus 4 pi over g squared. So it's the same exponential contribution as here. So there is this one single ambiguous term, and then there is this entire non-trivial, sorry, not in the mathematical sense. There's this whole non-trivial perturbative series here, which has a one instanton effect, which is completely invisible to the perturbation theory. If you do the analysis of the large order behavior of perturbation theory, it will tell you about this term, but it will not tell you about this F1. And you can see this already from the fact that the leading order, this one is indeed ambiguous and this one is not. Now you could expect that maybe there is some hidden complication at higher by playing around with the larger behavior of F0, but we have reasons to believe that really F0 does not evidently see F1 once I talk about the theta angle. But of course, there are some interesting relationships between this, which will not be the purpose of my talk. And this difference here, we suspect that is because in the O3 sigma model, this effect is a stable instanton, while in the O(n) larger than 4, where we just got the other trans series, the instantons were unstable, so they have these negative modes. Now, the thing is, the Bethe Ansatz really is somewhat indifferent to the specific physics of the model. It just knows the exact solution and gives us this trans series. It is now up to us to decode from our more conventional quantum field theory methods. We have to, in a way, interpret these results that come from the Bethe Ansatz. The Bethe Ansatz just cares about what is the solution. It is now up to us to sort of decode these things. So an interesting challenge, which has still not been done, would be, can one calculate this F1 from perturbation theory around an instanton in the O3 nonlinear sigma model? So this is a calculation that is yet to be done, but one would have to do these checks then to really check that these readings of instantons and renormalons really do make sense. Because from the Bethe Ansatz point of view, it's just giving you trans series. It's just a solution. The physical interpretation of the solution is now up to us. But of course, in physics, it's always better to solve a problem once we know the answer. So now we have the answer. It's up to us to figure out how to solve the problem in a generic QFT. Some other examples now, the Gross-Nouveau model that has already figured a lot. Here I'm assuming n to be strictly larger than 4. This has also already been discussed. Now we have this leading IR renormalon, which is almost universal. It appears in almost all of the models. And then we have these singularities, which survive large n, but they have this weird rational number, n-2, n-4. So they seem to be renormalons, but there's something is going on here. This trailer for episode 3. Now some other models. Now the supersymmetric O(n) nonlinear sigma model has both. So it has these instanton-like singularities and these renormalon-like singularities. And in the function sigma, you have them separately, but as you do your calculations in this method and you have to manipulate all these series, they all get mixed up. So a priori, you could have a 3 renormalon plus 2 instanton term in your trans series. A priori, this can happen. So you can have any linear integer combination of these two. The SUN principal chiral field also has, now this one does not have the II renormalon from some very specific cancellation, but the SUN principal chiral field has all three. So it has the II renormalon, it has these special renormalon looking things, and some instanton looking singularities. And they can have, and these two always mix up. This one is always isolated. It's just a very, it really only appears in the final calculation. So it does not get, sorry, there's a question. Yeah.
The location for the special renormalon.
Yeah.
How dependent on that? How is that dependent on the choice of chemical potential?
That's a good question. So it is not very easy to do this calculation with different Qs. With the case where we have done the calculation with two choices of Q is the principal chiral field. And so far, what happens is with one choice of Qs, you get all of them. And there, if you do a different choice of Q, these ones do not show up. So we really have not tested this. So as far as we can calculate, the different choices of Qs seem to make things appear or disappear. We have not yet found like two completely different renormalons in different choices of Qs, but this is not something which I must confess, for most models, we just do one choice of Q. So I cannot give you a lot of examples to back this up. And there is this model. Let me just mention, there is this, one can also study the principal chiral field, but where the target is not SUN, but SUN modded out by SON. From a physical point of view, you can think about it as gauging the action of SON. This model is the physics is very similar to the SUN principal chiral field. I would just like to point it out because I will use it later. And again, it has a similar structure. So it has weird renormalons, instanton-like, and some IR renormalon. Now, okay, so we get all this information. Can we still, we want to get more information of what is going on physically with this trans series. So maybe we can start forming these models in interesting ways. So one interesting non-perturbative thing that you can do with these models is to add a theta angle. So a theta angle, if you're familiar with the theta angle in QCD, this is very much the same way that you can think of these models as toy models for QCD. One can almost think about it as this theta angle has a toy model for the QCD theta angle. If you're not familiar, it's a term which is purely it's a topological term, and it is purely non-perturbative. So this term, once you add this term to the Lagrangian, so it's I theta times this Q. Q is given by this quantity. This term is purely non-perturbative. Perturbation theory is completely ignorant to this term in the Lagrangian, and it is essentially a topological charge. So if you think about the O3 sigma model, it's a model from 1 + 1 dimensions into O3, into essentially the two-dimensional sphere. So you can think about it as a model where the fields are maps from the sphere to the sphere. And so in the same way that maps from the circle to the circle have a winding number, there is an analog of the winding number from spheres to spheres, which, of course, this is the degree in mathematical literature, and more generally, this type of topological terms are related to the second homotopy group. And so essentially, this is some sort of winding number of the field configuration. And so because there's a very global property of the field configuration, it's just missed by perturbation theory, but it has a non-perturbative effect. And in particular, for the very specific value of theta equals pi, the model is still integral. Because if theta is not equal to pi, you do lose integrability. Because this does affect the exact S matrix. So if theta is not precisely pi, you will lose integrability, but at theta equals pi, you recover integrability. Now, this theory at theta equals pi is an extreme. O3 with theta is on its own, so a very interesting theory. I will not expand on all, but just for the more interested, while O3 is a gap theory, so in the IR it flows to a trivial theory. The one with theta equals pi is actually gapless, and it flows to a non-trivial CFT. So it's a theory on its own. It's very interesting. But for us, we're mostly just thinking about it as a deformation of the O3 case. So what happens? So just from instanton calculations, one can show that an instanton configuration, the action of an instanton configuration, has this very nice exponent. The action of the instanton configuration will be this, and it is related to the topological charge in a very nice way. So essentially, when theta equals pi, it picks up a minus sign depending on the number of instantons. So the one instanton will pick up one minus sign, the two instantons picks up a plus sign, and so forth. So it has this very nice relation. Again, if you have seen there's an analog result in QCD, this is very similar derivation. And this is exactly because integrability is preserved, we can use our methods in the model with the topological angle. And this is exactly what the Bethe Ansatz gives us. So we get this F1 term, which I was associating with instantons. When you do this in the model deformed by the theta angle, it picks up a minus sign. So which I rewrote as cosine of theta. And one can even extrapolate that maybe, and here I'm purely in conjecture land, maybe this trans series even holds for intermediate values of theta. Now, this is purely a conjecture. Maybe this is one of the simplest things that you can conjecture because F1 would naively expect to be real. So this is one of the simplest things one could conjecture for intermediate values of theta. And I'm writing this here because there is this quantity called the topological susceptibility, which is essentially the second derivative of the free energy with respect to theta. And this is something that can be calculated in other ways. So for example, people in lattice field theory calculate these type of things. Can calculate these type of things. I mean, in this particular setup is not been calculated yet. So here we have a very particular, we have a conjecture for this physical quantity, which is interesting, this O3 model is a model that shows up in condensed matter and all other things. So this is a model which is interesting on its own. And from this trend series, we have this conjecture for the topological susceptibility, which if ever anyone knows how to calculate in a different way, or perhaps if you figure out a different model, a different way, one new different way of getting this object, this would be an interesting test of this trend series that we get. But at theta equals pi, this is the trend series that we get. Again, it matches a numerical solution of the integral equation, and so here it does seem to match this into what we would expect if this sector was indeed an instanton sector. However, things are actually yeah, sure.
Would that imply that there would be a resurgence relation between distinct topological sets?
Not entirely sure. Not entirely sure, because actually, I mean, our interpretation of this is actually since the theta angle does not change perturbation theory, and when you turn it on to pi, just completely changes the sign of this. What I suspect is that this is hinting at that maybe F1 is really invisible to F0. Because you have these two theories that have the exact same perturbation theory, and F1 changes by a sign between them. So this does seem to hint that maybe F1 is hidden in some way from perturbation. So if I just gave you the perturbative data, you could be in any of the theories. So, and perhaps there is still a clever way. I mean, perhaps there's still a clever way to reconstruct just from perturbation theory. But yeah, this does put some, let's say, some cogs here, some difficulties here. Curiously, this term here, and this just follows from the Bethe Ansatz, this one does not pick up the minus sign, and that is important. That of course is an important consistency check. If this, because F0 is the term, if this one had picked up a minus sign, everything would go bananas. The final result will no longer be unambiguous. So fortunately, this one does not pick up the minus sign, only this one. So the Bethe Ansatz really knows what it's doing. The reason why I mentioned this coset model before is that the coset, you can also put a theta angle in the coset model. Now, you cannot put a theta angle in any arbitrary model and have interesting results. I will not go into the technicalities of it. It just has to do, if you want, it has to do with the topology of the space where your fields take values. If you know a little bit more about topology, basically you need to have a non-trivial second homotopy group. But the point is that just some models can have non-trivial theta angles and some just can't. And the SUN over SON coset sigma model has been exactly constructed by Paul Fandley to allow a non-trivial theta angle. So, but it can only take values of 0 or pi, otherwise it's inconsistent. But integrability is preserved in both cases. So here it's a model where we can turn on a theta angle to pi. We still have integrability, so we can still use our methods. But now, if you recall, this coset sigma model had both renormalon-like singularities and instanton-like singularities. And while for instantons, we had some expectation of how they should behave under this theta angle, for renormalons, I think this is genuinely a new result. I mean, well, there were people that suspected this, but I think this is a genuine new result of what happens to renormalons under a theta angle. And what happens, curiously, is the exact same thing that happens to instantons. So if we just take the leading non-perturbative term, we have some real part and some ambiguous imaginary part that cancels ambiguities coming from perturbative series. And in the theta angle version, the real part picks up a minus, and the other one, fortunately, remains the same. This is good because the perturbative series is still the same. So what? Yes?
When you say that you're talking about the real part, when you say unfixed, you mean unfixed by perturbation.
Yes. Yeah. Yes. Yeah. Precisely. Yes.
And you know what the value of C1 is.
Yes. Yes. Yeah. From the Bethe Ansatz does give you the C1, and the numerical solution does. Yes. Yeah. No. But thank you. This is yes. Exactly. So it is unfixed by perturbation theory. So this part changes sign, and the other one remains the same. So this is exactly what one wanted from consistency reasons. And so this is an interesting new information about renormalons. Now, what does this say about renormalons? It's not entirely clear, because renormalons seem to be in some way related to these non-perturbative IR properties of the theory, and the IR of these theories under a theta angle changes completely. Again, the O3 nonlinear sigma model again, perturbation theory, it's more or less independent of whether there's a theta angle. So the UV behavior of the theory is similar, but the IR behavior is completely different. Without the theta angle, you go to a gap theory. With the theta angle, the IR is some non-trivial CFT. So perhaps renormalons are sensing what is going on with these IR. So this is the technical result. This is what happens to the trans series. We don't have a physical interpretation of it yet, but I think it's an interesting result. Now, let me just do some quick comments about this discussion of how we can apply resurgence in this model. So this is the final final discussion in Marco's talk. Here, let me use this nomenclature from the paper of Lorenzo Di Pietro, Marco Ceroni, and Marcos Marinho and Giacomo Fabrieri, of calling these, just labeling these ideas, weak resurgence, strong resurgence, and something I'm going to call very strongest resurgence, let's say. So weak resurgence is just the idea that these observables in quantum field theory can be rigorously defined as the Borel summation of trans series. And so far, our results do validate this. The things that we got out of the Bethe Ansatz are trans series, and when we Borel resum it, as far as we can tell, we get the exact results. Now, there's a stronger sense of resurgence, which is that yes, these apply, and we can get the structure of the trans series just from studying perturbation theory. So this is more or less what we usually like to do, right? We want to study the larger or behavioral perturbation theory, and from it deduce the structure of the trans series. Maybe I mean, there are things that we cannot fix with perturbation theory, of course, but we can get the structure of the trans series. So I'm going to call the cases where this happens strong resurgence. So you could, if you only knew perturbation theory infinitely well, you could figure out the structure of the trans series. And I'm just going to call. But fix the topological sector, right? Yes. No. Here I'm going general. Now I'm zooming out and just looking at all the models that we've seen so far, just to discuss a little bit what we see about the patterns of resurgence, let's say, that we see in these different models. And of course, there's also, of course, a dream that maybe, you know, just median resummation of perturbation theory would be the final answer. Of course, this would be nice, which I'm going to call strongest resurgence. So this would be, you really only need perturbation theory. This would be nice, but of course, one can already see that maybe this is too nice. Okay, so in general, most models that we study satisfy strong resurgence. They see, at least as far as we can test, they seem to satisfy strong resurgence. Not all of them, but most of them. But they do not satisfy strongest. So there are things that medium resummation would miss. So this real part of C1, of course. In particular, this seems to happen particularly in models with models with these weird renormalons are the ones that more clearly do not satisfy the strongest case. Perhaps Janusz will talk about this. For example, in the O and sigma model, usually the difficulty with the strongest is only this II renormalon, and then the other instanton singularities, in many cases, do not seem to then cause other problems. But in general, so we have strong resurgence, but not strongest. This is the general statement. The exception to this is the O3 model. So the O3 model, as far as we can tell, might not satisfy strong resurgence because of this problem with F1. So one could hope that maybe once we figure out the IR renormalon, maybe median resummation works for the rest. This is a hope. This, for example, in the O4 model, this is true because there the IR renormalon does not actually obstruct strong resurgence. So, but I will let perhaps Janusz discuss this a little bit. And now, of course, how does this connect with large N? Because the trans series that we got here were finite N. So we have results at finite N, and so we can take our finite N results and then take the large N results and compare them to the discussion that Marco was just having. And so it does seem that, for example, in the Gros-Nouveau model, at finite N, you seem to have strong resurgence. There is this problem that Marco was discussing with the next to leading order, with the already happened at the first exponentially suppressed sector, that there seemed to be some issues with resurgence at next to leading order. At finite N, there really is no issue. It really seems that there is something that breaks when you take the large N limit. So these difficulties with the strong resurgence that Marco was mentioning, they only happen once you take the large N limit. At finite N, the Gros-Nouveau model seems to, you seem to be able to get the structure of this trans series just from perturbation theory. So this ties, so this makes the connection with the previous talk. Now, Ricardo, I have some comments on condensed matter models, but maybe 5 minutes. Okay, so let me just bolt quickly through the condensed matter results. Maybe you saw this last year. So there are also non-relativistic systems where we can apply these methods. So the Godin model is it's a one-dimensional model. So these are spin 1/2 fermions, or we can take it spin. We can have it with n spin components. So this is essentially the analog of the Gros-Neveu model, but non-relativistic. These are just fermions on a circle. This is a condensed matter problem. So there is no running of the couplings here, for example. And the ground state is just described by this version, which is essentially the grandfather of the integral equations that we were discussing before. So this is the Godin integral equation, and in fact, its predecessor is the Lieb-Lineker, which is an analog model of this. So we can also apply this, or we can also apply our models here. So last year I talked about using Volin's method here, and you would get this large order behavior. But now with our trans series methods and this Vinderhoff formalism, we can get the trans series in this model too. So we can, for example, we can already find the trans series term that compensates for this, and we do get. And here, what do we get? And here, I'd just like to mention this because maybe this is related to some physical intuition about renormalons, which will. So take this as a prequel to Ramon's talk, which is in these models, this pi square over gamma, the non-perturbative physics that it's hinting at is the superconductor gap. So in these models, the ground state is gapped because essentially instead of having free fermions, the ground state really is a model of these are attractive fermions. So they pair up, the spin up and the spin down. They make a bound state of 2 fermions, and the ground state is more akin to a free gas of these pairs rather than free fermions. And if you have n components, it will be a bound state of n fermions. And so this delta BCS, so that's the gap, it's pi square over 2 gamma. One can generalize this to have some dependency in n. And so this pi square over gamma is exactly what we're getting in the trans series. So the Borel singularity was noting the BCS gap squared. So in a way, what is happening is that perturbation theory breaks down at the scale where this non-perturbative gap becomes relevant. In a way, this is not too different from what happens in the field theories. This IR renormalon, at some point I rewrote it as m squared. It is also the IR gap of these theories, which is curious because this IR gap, perturbation theory really doesn't know about it. If you do perturbation theory in the ON sigma model, the bare Lagrangian does not know about this non-perturbative gap, but the Bethe Ansatz does know. So this is part of this highly non-perturbative IR information that the Bethe Ansatz has, which it then encodes in the trans series, that perturbation theory only senses through resurgence. In the particular case of these condensed matter models, we can associate this with a factorial divergence from ring diagrams. So this is actually a renormalon effect. This seems to be a renormalon effect. And this is a theory where the couplings don't run. Now, as for renormalons in field theories, I'll let Ramon discuss them on his own. And so let me wrap it up. So, of course, well, this part, I think it's an easy sell to this audience. This part is going to be told, is the next talk. Sorry, this slide clearly was not massaged enough. This was perhaps the key idea that I talked about today, which is really integral models are very interesting models to do for this, because we can get non-trivial results that we can learn a lot, so we can know the answer. In integral models, we know the answer. In a way, the Bethe Ansatz is the answer, and now we can do physics to understand the answer, or one can try to look at the interesting resurgence properties of these results, because our method is still clearly only the very beginning. It would be very interesting to generalize this method. If we could push these methods to get higher orders in perturbation theory and non-perturbative effects, it would be really interesting. And clearly what we're doing, clearly what we did with this model with these methods is not the end. It's not the end of what this formalism allows. One should be, for example, this Volin's method, it gives us the perturbation theory. Is there any way of incorporating it to also get the non-perturbative effects? So clearly there's still a lot of resurgence work to be done in these methods. And of course, I think the really long-term, long-term, or let's say medium-term, medium-long-term goal would be, can we reproduce all of these trans series from conventional quantum field theory methods? Can we get these F1 from an instanton calculation in O3? Can we get these renormalon sectors from, I don't know. This is I think that really want to, all these trans series should be calculable from regular quantum field theory methods. And now that we know the answer, we can try to solve the problem. And with that, I wrap up. Thank you.
One super fast question.
Just in your slide, when you summarize the types of resurgence,
Yes.
In the case of strong resurgence, you said these coefficients in the trans series that you determine using numerics. So obviously in the integrable case, you can determine them exactly.
Yeah.
But the numerics, so does that mean you do a lattice approximation, or what do you? What can you do?
Yeah, so in our cases, the way one would fix them with numerics would be using the integral equation. In a general QFT, maybe it would have to be lattice or even experiments. This could be a conceivable status quo, right? You would get the trans series from the perturbation theory, and then maybe you would have to fix some things with a lattice. And of course, if one could get everything from the path integral, it would be nicer. But it would maybe it would still be an interesting point if one could just do lattice or experiments. So yes, I'm thinking more or less in that direction. Yeah.
Okay, we're running a bit late, so
Yes,
let's
sir.
thank Tomas again. And please be back 11:30 sharp. Okay, so we have a slightly shorter coffee break.